Hello and welcome to UGC E-PG Pathshala. I am Dr. Karunashri, Assistant Professor, Department of Geography, Kirodi Mal College, University of Delhi. Today, I am going to discuss with you the module Earth Movements, Epeirogenic, Orogenic, Cymatogenic, which comes under the paper Geomorphology. The objectives of present module will be: number 1, the introduction with the concept. Second, understanding earth movements, type of earth movements, epeirogenic movements, orogenic movements, cymatogenic movements. Now the introduction. Earth's surface is not stable but is changing constantly. None of the landforms found on the Earth's surface are forever. There are various geomorphic processes working on the landforms. These processes were working in the past and also working present. The Earth's crust is influenced by both internal and external forces, which may affect the Earth on both major and minor scale. Internal forces may include upliftment, contraction, expansion, disruption, distortion, and outpouring. External forces would include forces of denudation like weathering and erosion. The description of the landforms cannot be explained only through these forces, since these changes are so slow that they go unnoticed. But when these changes are sudden, like volcanic eruption, landslides and earthquakes, we can observe and notice these changes. The present landforms are a manifestation of complex and intricate interaction of Earth's material facing resistance on one hand from the tectonically and climatically derived forces. Earth movements, as we already know that Earth's crust is constantly affected by the internal forces. The main cause of such internal forces can be the radioactivity originating within the deep interiors of the Earth's crust or substratum and the resultant convection current caused by it. These convection currents causes the crust to move, which further causes sudden and rapid movements like earthquakes, or extremely slow movements like mountain building and continental building, which may take millions of years. These movements can cause upliftment, warping, turning, twisting, tilting, fracturing, subsidence and distortion of crust, and some may even cause squeezing of the rocks, which would give rise to high mountain ranges. Third part is types of earth movements. There are broadly two kinds of forces that causes earth movements: exogenetic forces and endogenetic forces. Please refer to figure 1 for these, which shows a chart of different types of earth movements. Exogenetic forces or exogenic, epigene, these exogenetic forces is mostly destructive forces, which through various processes would try to change the various relief features on the Earth's surface by smoothing, carving and molding these features. Endogenetic forces, endogenic or hypogene, are basically the forces which in Greek endo means within the genera or origin. Endogenetic forces can give rise to various structural features on Earth's surface, which are related to upliftment and subsidence, folding, faulting, fracturing and volcanic eruptions. All the landforms and relief features found on the Earth are formed of Earth's material. The landforms are formed because of various geomorphic processes operating on and beneath the Earth's surface at different rates. The exogenic processes derive their energy from Earth's internal or endogenetic forces, which gives mobility to the Earth's crust, which can also be called tectonism, and from the climate, which takes further help from the sun, which is its driving force. And endogenetic movements can be of two types: diastrophic and sudden movements. In Greek, diastropos means turned, twisted and distorted. Diastrophic forces are the ones that generally originate from deep beneath the Earth's surface and act as vertical force and work against the exogenetic forces like gradational processes. They disrupt the process of reducing the earth to the sea level by forming various landform features on it. First kind of differential forces can be classified into three categories. First is tectonic, second is isostatic and eustatic, third is eustatic. Within diastrophic forces, tectonic in Greek means builder. Tecton in Greek means builder. In the most commonly used word, it has very wide connotations. Tectonic movements can be epeirogenic movements and orogenic movements. These energy forces which emanate from within the Earth's crust include nepo-isotastic or crustal warping within the mantle, which is also called eperogenesis, earthquakes, and folding, which is also mountain building or orogenesis. Faulting or metamorphism due to heat flow and volcanism. Endogenetic process receives less importance in geomorphological studies, but these forces are increasingly gaining importance and appreciation because of the effect of such movements in certain areas of the world such as the circumspecific belt and areas of young fold mountains. They are expressed and studied for the earthquake activity and in volcanicity in the said areas with their important influences on such areas. In such areas where the endogenetic influences are more powerful can alter the changes brought by the exogenetic processes. Gilbert had defined epeirogeny as the process of continental building. In parallel to this, he had defined orogeny as the process of mountain formation. These two sets of processes differ enormously in the scale of space and time. In many regions of the earth where the vertical crustal movement is very slow and is measured in millimeters per year, that is 1 millimeter per year, which is equal to 1 meter per 1000 years, which is equal to 1 kilometer per 1 million years, have persisted throughout late Cenozoic times. The rate of cumulative uplift has outpaced erosional lowering. Such tectonic geomorphology is associated with the construction of the landscapes. These are regions of erosional landscapes in which the tectonic origins are still obvious. Figure 1 shows a chart which explains the division of the major earth movement. Epeirogenic movements are the ones which operates vertically from the center of the earth to its surface caused by radial forces or convection currents. You can refer to figure 2 for this. It causes regional upliftment, but on a large scale, therefore not much noticeable deformation of the surface take place. In green, Epeiros means continent. They are very wide and large scale movements spreading over the continental platform or the stable block of land. Therefore, these processes are also known as continental formation. They are characterized by broad, gentle and widespread warping, subsidence, upliftment, emergence, submergence of large areas. These movements are so slow and widespread that no obvious folding and fracturing can be seen in the rocks. Bloom has defined epeirogeny as continental vertical tectonic movement of low amplitude relative to its wavelength, not within an orogenic belt, that does not deform rocks or the land surface to an extent that is measurable within a single exposure. And this broad regional tectonic movement with no local deformation can be either positive movement like upliftment or negative movement like subsidence. Upliftment movement causes the upliftment of the continental masses, either whole continent or the part of it. It also causes upliftment of the coastal land of the continent. Such type of upliftment is called emergence. Subsidence of the continental masses again happens in two ways. One is subsidence of the land area called subsidence. Alternately, the land near the sea coast is moved downward or is subsided below sea level and is thus submerged under sea water. Such movements are called submergence. Glacial isostasy is one more kind of epeirogeny, in which the reason for the regional subsidence is the weight of an ice sheet. Deglaciation as a result of the removal of this load and post-glacial recovery has resulted in its discovery. Did you know these large-scale movements were prevalent in all continents of the Earth's surface, including Antarctica? Various evidences have proved both upward and downward movements since Precambrian times. For example, presence of marine sedimentary rocks of Paleozoic, Mesozoic and Cenozoic age, which lie on all continents upon the much eroded older rocks. Epeirogenic landforms. Prevailing isostatic equilibrium has maintained the average continental crustal freeboard within less than 100 meters of sea level throughout Phanerozoic geologic history. The freeboard of a continent is the amount exposed above sea level. These freeboards are supported by isostatic buoyancy. If a continent has crustal thickness as just 30 kilometers and density of 2.8 grams per cubic centimeter, it will not be having any freeboards but will be at isostatic equilibrium just at sea level. Only at the orogenic belt where the crust is more thickness, otherwise continental crust is typically not thicker than 33 kilometers. Therefore, even the minor changes in the sea level owing to the epeirogenic movements can lead to the flooding of extensive areas of the continent and deposition of the layers of sediments. There are many examples to prove such kind of subsidence. For detail, refer to module 8. Over a very large area of the continent, one can find sedimentary rock of 1000 to 2000 meters in total thickness. These rocks are undeformed marine sedimentary rocks which overlay over igneous and high grade metamorphic rocks of the continental crust. They are as old as the early Paleozoic era. These sedimentary rocks are like platform separated by disconformities that have only minor relief. They were never high enough above sea level to be subjected to deep fluvial dissection. These platform sedimentary rocks are almost in their initial depositional altitude are almost completely eroded from its continental landscape before any relief feature of significance can emerge over it. In such landscape, erosional features like broad structural domes cover crust and basin with the epeirogenic tectonic relief of a few hundred meters over distance of hundreds of kilometers are common, whereas the submergence of strata is very less and undetectable, usually less than 1%. At the central region, topographical basins are formed when these epeirogenic domes are subjected to erosion. The rate of tectonic upliftment is extremely slow and less compared to the rate of erosion. The result is a topographic inversion by erosion on epeirogenic structures. Movement of greater magnitude are to be seen by the sedimentary succession built upon the continental shelves within the continent themselves. Vast depression is recorded toward the end of Cretaceous period with series transgressed sedimentary deposited in epicontinental seas. On the stable block of the continents, one can notice the various kind of sedimentary deposits. They could include aeolian deposits, lacustrine deposits, coal, evaporates and utilities, also the archores formed out of decayed uplifted mountains. A sequence of such long continuous deposits can be seen in the interiors of low and stable continental margins of the Karoo sediments of South Africa. Lake Victoria and Lake Kyogo in East Africa is another example illustrating the shallow basin with sinuous outlines indicating drowning of land. Cratons, also known as continental cratons, are the extensive continental crust or shields. They are a complex of deeply eroded, accreted, organic terrain and can be ranged to various ages. It has crystalline shields or platforms of thin, old sedimentary rocks, which monotonous, low altitude and low relief not far above the sea level and can date back to many centuries. About 1/3 of the subaerial landscape is eroded from exposed and ancient igneous and metamorphic rocks of the continental crust without any sedimentary cover. They are exposed rocks which must have solidified from magma or metamorphosed at depth of 10 to 20 kilometers or more. For example, present relief on the Canadian Shield continues as an unconformity under the Paleozoic and Mesozoic sedimentary rocks on its periphery. The Australian Craton is a region of exceptionally low relief and tectonic stability with landform alleged to be 10 to 100 million years old. Figure 3 refers to, you can refer to figure 3 which shows Australian cratons. If cratons are such large low-lying platforms of thin old sedimentary rocks, then what tectonic processes could cause the epeirogenic uplift of other large continental areas? A very characteristic behavior of a craton is long continuous rise of localized plateau. The local circulation causes elevation. These elevations are caused by mantle plumes deep beneath the areas of continental crust or due to collision of two continental plates. This elevation can be as fast as 8 millimeter per year. The uparching of the continental crust by the hypothetical plume head may also have caused the surface rifting and volcanism in the Columbia Plateau and Snake River Plain to the north of America. This plume migrates to the west with its tail fixed in the mantle. Therefore, it appears to have migrated eastward from Columbian Plateau to its present position under Yellowstone Volcanic Plateau. Did you know? The west of Yellowstone National Park covers about 8,000 square kilometers. The area is rising slowly at the rate of about 3 to 5 millimeter per year. From 1955 to 73, the central Adirondack in New York State rose by 40 meters and its northern margin subsided to about 50 millimeters. The rate at which the Rhine Massif is rising is about 0.35 millimeter per year. The Colorado Plateau have risen for about 550 millimeter at the rate of 0.1 millimeter per year in the late Cenozoic, and the Deccan Plateau in India has uplifted in tertiary and quaternary and continues at the present time at the rate of 0.36 millimeter per year. Fifth point is orogenic movements. Orogenic movements are the ones which work horizontally to the surface of the earth, like tangent to the surface of the earth. Therefore, they are also called tangential forces. These forces work in two ways. First, opposite direction, which means tensional force or divergent force, and second is towards each other, which means compressional forces or convergent forces. Such tectonic geomorphology is associated with the construction of the landscapes. The rate of the crustal movement can be measured in millimeters per year. That is 1 millimeter per year is equal to 1 millimeter per 1000 years is equal to 1 kilometer per 1 million year. The result of these strain and stress of the rock have produced are great folded ranges of mountains, and therefore it is called Oros, which in Greek means mountains. There are many regions of the earth's surface where the vertical crustal movements have persisted throughout its Cenozoic time. The rate of cumulative uplift has outpaced erosional lowering. Such tectonic geomorphology is associated with the construction of the landscapes. There are regions of erosional landscapes in which the tectonic origins are still obvious. Constructional landscape of such region is called tectonic geomorphology. Orogenic clearly refers to mountain formation. Unfortunately, in geologic usage, the term has assumed much more complex and contradictory implication. Gilbert in 1890 formalized the term displacements of the earth's crust which produce mountain ridges are called orogenic. Now we can come to compressional forces, which involves first crustal bending. When due to horizontal movement which is working towards each other, crustal rocks are forced to bend, it is called crustal bending. It can be of two kinds: warping, that is when the large area of the earth's crust is affected by crustal bending. When the crust is bending upward, it is called upwarping, and when the crustal bending and the crustal part is bending downward like a basin or depression, then it is called downwarping. Second is folding. When the crust is layered and bedded with sedimentary or igneous rocks and already have a pre-existed rock structure. In such cases, a slight fold in any such structure would result in a wave-like structure. The up-folded rock strata is called anticline and down-folded strata is called syncline. The two sides of the fold are called limbs. This can be seen in figure 5. The axis of the syncline and the anticline are called axis of syncline and anticline, and areas in between them is called axial plane. You can refer to figure 6. Different kind of fold depend upon different factors like nature of the rocks involved, like elasticity and rigidity of the rocks, intensity and duration of the compressive forces, which means magnitude. Differences in the elasticity and the magnitude give rise to difference in the inclination of the limbs. Symmetrical folds. Symmetrical folds are both limbs when the both limbs are inclined uniformly. Asymmetrical folds are when both limbs are inclined at different angles. Monocline folds, when one limb is inclined moderately and one is steeply inclined. Isocline folds, when both limbs become parallel to each other due to immense force but are not horizontal. Overturned fold, when the limbs folded beyond vertical and turn so much that both the limbs bend in same direction. Recumbent fold, when the compressive force is so strong that both the limbs bend and become parallel to each other. Nepes, when the pressure of the compressive force continues and as a result the root of the one of the limb is uprooted and thrust on the opposite limb. Now we come to tensional force. Tensional force and faults are formed due to fractures in the crustal block and their displacement. Fault plane is the plane along which the vertical or the horizontal displacement take place. Upthrown sides and downthrown sides are the two sides representing upper block and the lower block respectively. Angle between the fault plane and horizontal plane is called fault tip. You can refer to figure 7 for this. The direction of the displacement of the crustal block defines the type of fault. which can be dip-slip fault or strike-slip fault. Refer to figure 8. Normal fault. When the tensional force pull apart the crustal block in the opposite direction, down-dropped block is the graben or rift. Upthrust block is a horst. Reverse fault. When the movement of the fractured block is towards each other due to compressional forces, hence also called compressional fault. Refer to figure 9. Lateral fault, also called strike-slip fault, is when the displacement is horizontal. Refer to figure 10. Step fault, series of fall with their slopes in one direction. Now we come to mountain and orogeny. The process of mountain building runs in a cyclic motion which recurs periodically throughout the geological time scale. Between two periods there can be long periods where the earth's crust remains relatively stable. All orogenic belts are on or near converging plate margins. The plate boundaries can be wide if they are embedded within the continents, as in the Central Asia. Mountain ranges embedded within the continents such as the Himalaya mountains and the Ural mountains of Asia have been shown to have been near plate margins at their time of formation. The new continental terrains are accelerated to them later. In orogenic movement, it is not necessary that vertical movements are more rapid than the broad regional movements. However, they seem to be more continuous through time. It is to that not all orogenic movements, orogenic mountain belts are randomly placed but are in some distinctive pattern over the earth's surface. Even though there is no direct relationship of the earthquake zone area and the orogenic belt, but we find circum-Pacific belt associated with the active volcanoes along subduction zones. Three distinct types of orogenic belts can be identified on converging plate margins: island arcs and trenches along thousands of kilometers of western Pacific margins along Indonesia. In the Caribbean Sea, there are subduction zones between two portions of oceanic plates or lithosphere. The plate which is drowning flexes upward in a broad outer and swells seaward of the trench, into which it descends beneath the overriding plate. When the plate submerges, it rubs within inner trench wall and scarps the accumulated sediments consisting of deformed mudstones and sandstones. Many times such deformed sediments rocks rises above sea level to form frontal arc of mountainous island. Volcanic arcs of andanistic composite cones can follow island arcs. The upper plate spreading in response to the buoyancy of the subduction plates. For this you can refer to figure 11. Second is Cordilleran type of mountain ranges. On the Cordilleran type of converging plate margin like the Andes mountain of South America, complicated mountain ranges evolve where the oceanic lithosphere subducts under thicker continental lithosphere. Narrow coastal ranges may be formed on the edge of the continent as a result of accretionary prism of trench sediment or to faulting and uplift of continental crustal block along with an elongate longitudinal valley. Parallel to the coast with older sedimentary and metamorphic rocks as the axial part of the belt, the volcanic peak on a Cordilleran type of mountain belt rises above a broad plateau. Due to heavy compression, the central mountain range becomes thick and continental crust makes it rise because of isostatic adjustment. The continental platform can later be folded and thrust towards the continental interiors. In the northwestern United States, the Olympic Mountains are part of the coastal ranges. The Puget, South Lowland and the Vidya-mitra Valley are part of the longitudinal valley, and the Cascade range of the volcanic arc. You can refer to figure 12 for this. Third is collisional mountain belts. Island arc or another plate of continental lithosphere, when due to convergence and subduction come into contact with the overlying plates of the subduction zone, create collisional mountain belts. Due to their low density, the island arcs and continental rocks, instead of going into the mantle, gets thrusted over each other, in the process forming high mountain ranges. High mountain ranges such as the Himalayas or Alps with intensely deformed rocks of contrasting lithology are good example. Refer to figure 13. For detail, kindly refer to module number 10. Fourth is extensional mountains. A fourth type of mountains are built by extensional and strike-slip plate motions in a variety of tectonic setting. Rift Valley formation is relatively localized and is considered a special style of orogeny. Continental breakups are characterized by an elongate swell or bulge along which the faulting generates, creating Rift Valley. Strike-slip faults are the cause of some of the most complex tectonic mountain ranges. The transverse ranges of Southern California have similar origin in their relation to the San Andreas Fault. Now we come to the sixth point, that is Cymatogenic movement. Geomorphic processes, both exogenetic and endogenetic, use Earth's internal energy as the source of power. These in turn are the base for the formation of all the landforms on the Earth. The atmosphere or the climate further modifies these landforms. Atmosphere and climate acquire energy from the sun. Hence, the landforms are not the result of just one force, but it is the result of extremely complex system of processes derived from interaction of Earth's material resistance on one hand and tectonically and climatically derived forces on the other hand. Endogenetic processes which emanates from within the Earth's crust and includes crustal or non-isostatic warping within the mantle, that is epeirogenic, and earthquakes, folding, which is orogenesis, faulting, metamorphism due to heat flow and volcanism. In 1959, L.C. King introduced the concept of Symatogeny, whereby a landscape often hundreds of kilometers wide is either arched or domed to thousands of meters with minimum rock deformation. According to King, modern mountain ranges are usually Symatogenic, not orogenic, and any local rock deformation is presumed to antedate the simple Symmetrogenicity that, followed by erosion and valley cutting, has created modern day mountain terrain. This brings me to the end of this module. Thank you so much.